Hello everybody, my name is Gabriel. Now I want to start out with saying that this will not be a practical presentation. If you're a practical person, if you like things like, what is this library and how do I use it, this will not be for you. And the reason why I want to do this presentation is because I think most of us, well probably all of us are, JVM language programmers, we, deal with Spring, and the sort of day-to-day is very, there's a very narrow field that we're all part of. And I think it can be very interesting to sort of look at what's on the other side of the fence and figure out hey, there are completely different languages that apply completely different principles and where people think completely differently. And I think it's useful to sort of, from time to time take a look at that because, excuse me, because I think that if you spend your entire life stuck in one single place, then to put it another way, if all you know is a hammer, then every problem looks like a nail, right? So I think, and there's you might have heard of Conway's law, which is a managerial version of this rule that I talked about right now, excuse me. And I think that it's important to, from time to time to look at something else and to, broaden your perspective. Now, that being said, this will be, I don't think it's necessarily complicated, but there will be a lot that we'll be covering. And I think your head will spin a little, and that's completely okay, but I have one request, and that is, at some points I'll need to go a little bit fast, and if I do, please ask questions, please raise your hand right away. I'll be very happy to answer them. So, how spicy will this presentation be? So we're going to start off a little bit easy, and that'll be pretty short, to be honest, and then we'll ramp it up a little bit. So let's start with the easy part. And let's start with DSLs. Hopefully, raise your hand if are all of us Kotlin developers? Raise your hand if you write in Kotlin. Okay, perfect. So hopefully this for you will be what do you call it, like opáčko, like a repeat, but let's see. So let's take a look at DSLs by example. So here we have a very simple config class. This could be like an HTTP config or something like that. And we're creating an instance of that. And right away, in 0 seconds, when you look at that, there's something that we don't like, that's not ideal. What is it? I hope you can see it. It's a little smaller than mutability. Perfect. That's for you. Oh, you got pizza. Okay, dessert. Right, yeah, exactly. Mutability. That's not perfect, right? Apologies for the small font. I thought it was going to be bigger. So let's solve that. And one easy way to do that is to just introduce a builder, right? I hope you can see it. Can you see it okay? Hopefully you can. So you introduce a builder, which in and of itself is mutable, and then that builder builds the actual config object, which itself is immutable. And you can basically keep that same syntax that we had at the beginning, so you can sort of do that apply stuff, and then you build an actual immutable object. Now, when we look at that, basically the last line, basically most of that is boilerplate, right? The whole creating of the builder, the applying of the lambda, and the build part, could be abstracted away. So let's do that. And let's define a config function, and let's put all of that boilerplate inside. And what we're left with on the last line is a very nice DSL-like kind of construct, right? But we didn't really do anything special. That's the main point I want to make here. All we did was introduce a builder and took advantage of Kotlin's, syntax rules, and that's all it took to actually create a DSL. So we could simplify that a little more. We could make that into a one-liner, and this is basically whenever you encounter a DSL, usually this is something that you will see. You will see some type of builder that will be applied to some sort of lambda that will be passed in, and that's basically what gives you your DSL function. I want to give you another example. Apologies for the immutable list here. This was originally presented to Java developers, and they don't know that list is immutable by default, so I need to make that explicit. But you can see that you can use even a builder function that we didn't actually define ourselves, mutable list, but you can apply this same sort of technique to it and get something that resembles a DSL. And this is actually a pattern that's so common that this build list is part of the Kotlin standard library, or has been for the past couple of releases. It wasn't there at the beginning. So the sort of general way that you approach DSLs is first You define a class that contains the verbs of the DSL. That's what you use to actually build it up. And then you define, and this class also contains like the intermediate results. So in case of the building up of a list, it would be, the list that you build up. If you defined like, say, a string builder or something like that, it would be the string that you build up, and so on and so on and so on. And then you expose a function, that's the config function over here, that's sort of, or the build list function over here, that exposes that DSL and actually builds up the result and returns it. So what the point I want to make here is that building DSLs is actually nothing magical, and it's very simple, and we actually do it every day. Whenever you create a class, any class, you're basically creating a sort of DSL that's used inside that class via its private and protected methods. So here's a final example. You might have seen that in the Kotlin documentation. This is a typical way of how you can apply builders to building up an HTML page, and you can, if you look at it, it's basically the same thing over and over again. So you can see the HTML that contains a lambda. Inside the HTML, there'll probably be some sort of HTML builder that'll have two methods. One method will be called head, the other method will be called body, and so on recursively inside. It's the same principle over and over and again. Now, for those of you who were present at the last meetup, which was sometime in June, I had a presentation about error handling. And this presentation is sort of a spiritual successor to that presentation. It's not a prerequisite that you were part of that or that you saw that one, but it is sort of a successor of it. And so I'll be making references here and there to it. I'll explain everything that's necessary. And the last presentation was about error handling, and this presentation will be about error handling as well. So the question is, can we build a DSL for error handling? Okay, this was the easy part. Now it becomes maybe a little bit complicated. So first I want to do a quick recap of the code that we actually discussed on last presentation. Let's see if I can, I probably can't make this. You probably can't see it, but I'll explain it. Hopefully we can communicate. So the domain that I was demonstrating this on is basically you have an account, you have some orders, and you have some pricings of the account. And your task is to calculate how much I should bill that account. And the way you do that is that you take the pricing from the account, and you take all the orders, and you basically, multiply the orders by some fixed amount, and that gives you the total amount that you should bill. So very simple example, or very simple domain. And we looked at some three functions where one was basically given an account ID, you want to retrieve the name, so that's basically nothing else than retrieving the account and accessing the name. You can see that on the first line, or hopefully you can see it. The second one is that you want to get the charge for a single order given an order ID, so you fetch the order. From the order you fetch the account. From the account you fetch the pricing. You do the multiplication. You get the you get the order value. And the last one is that you want to get the total bill for the account. So you get the account, you get all its orders and the pricing, and then multiply all of them together and sum them. And the example on the left is what you would see when you would write this using exceptions, if your error handling was exception-based, right? So basically all these methods that are sort of mocked somehow, get account, get order, get pricing, those would throw some sort of exceptions, maybe, record not found or database is down or something like that. But it's all sort of hidden because it's exceptions, and they would just bubble up and be dealt with somewhere else. And what we talked about last time is that there's a different approach that you can take. And the approach you can take is that you basically define what's called as either a result class, if you're from Rust, or it's called either sometimes. It's a sealed class or sealed interface that has two instances. One is everything was fine, okay. And the second one is some type of error happened. Now, Rust calls this result, and the instances are okay and error, so that's what you can see here, or hopefully can see on the presentation. Other languages, Scala, Haskell, probably some others as well, call it either, and it's either a left value, which signifies an error, or a right value, right as in correct, which signifies that everything went okay. And we showed that when you do that and you rewrite the code using that, basically using like if-else statements, if this is an okay value, then we extract the value, do whatever we want to do. And then we do some manipulation and extract some common features. We get a version where we have functions called map and flat map, which sort of evoke the functions that we probably already know on list. And that's not a coincidence, but that's not something we will get into. But, hopefully you can see, when you look at the code on the right versus the code on the left, like there's a big difference. It's not, reading the code on the right isn't super easy. And I teased last time, what if there was a different way to do that? What if there was a way to use the result-based approach where we return values, but at the same time didn't have to sacrifice a very different, very, very different looking code. And this was the example I demonstrated. And what I want to talk about today is how we can actually build this DSL. So, let's talk about what the semantics are. How does this DSL actually behave? So we have two basic parts. The first one is like the function that starts it all off that we talked about before. That's the result at the bottom. And we basically have only one single verb, and that's bind. And you can see the signature over here at the top. Now, the semantics of bind is, if I get to some point to a function that returns result and call bind on it, if that result is an OK value, everything went OK, then it extracts the value inside and assigns it here. So if get account completed successfully, this will be an OK containing the account. We'll extract it and assign it to the account, variable. But if it was an error, if an error happened over here, what it does, it shortcuts this entire block, the entire result block that we're inside, and returns that value in place of that result block. So it kind of sort of behaves like an exception. It short circuits everything. This code doesn't execute. The same over here. We get an order. If it's OK, perfect. We extract the order. If not, we short circuit this entire block of code, and this doesn't even get executed. So that's how bind behaves. Now, given that, I sneak peeked a little bit, do you have any idea, or does anybody have any idea how you could implement that? With a DSL, perfect. What would that look like? What would the implementation look like? So I sort of expected that there would be two categories, one category that didn't have any idea and the other category that would know arrow, exactly. But even so, like arrow, how is that? What is that?
It's just been a long time.
Okay, perfect. Any other ideas? No candy for you. So here's a possible, very simplified implementation. Now, when you look at this is like the important part over here. And when you look at it, it's basically doing what I described with words, right? So we're looking at, is the value an OK value? If it is, perfect. We're returning the value that's inside the OK. And if it's not, we're calling fail. And fail is defined over here. And basically what we're doing is we're just throwing an exception. But what's key here is that inside the result block that defines the entire, like the block that we're working inside, we actually catch that same exception. And if we do, we extract the value that's inside. We have to do this sort of ugly cast and return it as an error value. So in reality, it's a little bit more complicated. Like there are some things that we haven't talked about here that I'm not going to go into. Like for instance, if you had nested result blocks inside each other, then you would have to deal with that, and there are some other things. But basically, this would be something that could work. And we have a nice little bonus, and that's that we actually have that fail. We've extended our DSL to include this fail function that we can then use in this way. And so this is really kind of sort of imperative code. And this fail allows us to say, OK, quit this whole thing, just jump out and jump to the end and return whatever object we're passing into it. Sure, go ahead.
So basically, what you do in this, let's say, fairly common pattern, right? Like when you pass like error handler as a function parameter to inside of the DSL, then you try to catch that, whatever exception. In your case, you are using custom exception that wraps around the actual error, and then you just put it into that error handler, which happens to be the fail or left value of the result. And that happens implicitly behind the scenes, so that the happy path never gets to execute.
Basically, yes.
Exception in the way.
Yes.
Which essentially skips.
Yes, exactly. Now, there are a couple of, so like I said, there are some practical issues that I didn't talk about and wouldn't talk about. Feel free to ask them about them at the end of the presentation. But there are other issues that are sort of more glaring that I want to mention. Now, the first thing is that essentially what we're doing is that we're using exceptions for control flow. And that's something that you should not do. At the end, I'll mention an article that explains, I think, really nicely why that's a bad idea. But TLDR, basically, exceptions can behave like goto if misused. And if you use them explicitly as the goto they are, then you're basically using goto. And we all know that goto is not a good thing that we should be using. Another problem is performance. Like exceptions are expensive when they're not used exceptionally. So when you like if you just throw an exception here and there, that's completely fine. But when you if you would mass throw 1,000 exceptions or something like that, that would have a measurable impact. And there are actually two parts to why exceptions are costly performance-wise. And again, I don't have time to go into that. You can ask me at the end, or I'll link an article. But the two parts basically are stack unwinding. That's one part, depending on how deep you are in the stack and how far up you have to unwind up the stack to find the error handler. And the other one is the actual capturing of the stack trace. These two parts are what make performance expensive. And finally, like the entire tone of the presentation, or the last presentation I made, was let's not use exceptions. And what I'm saying right now is let's use exceptions to get rid of exceptions, which is, kind of fishy. But notwithstanding, we can actually solve these, or these are actually solved. The not using exceptions, or the using exceptions to get rid of exceptions, is actually okay because we're only using them locally. They don't actually leak out of the implementation of the function. Which means that as an outside user, I don't get control snatched out of it. I don't have to deal with the fact that I'm calling some function and maybe that function won't return and instead will just jump to some error handler somewhere. So it's basically something similar to like break or continue in for cycles, or in while loops, or just regular loops, where we also jump to some point, but we always stay in the confines of that loop. And performance can also be solved because you can suppress stack trace creation, which is the one part that I talked about, and the other part is related to how deep inside the stack trace or inside the stack you actually throw the exception. But if you use inline functions in Kotlin, then you can flatten that, and that becomes actually very, very cheap to do. Now, what you mentioned about error before, this is only one way that you can implement it. There's an alternative way that uses continuations. This is something that I originally wanted to make part of this presentation, then I decided not to because it's a complicated topic, and I think it would deserve its own presentation. So I'll just mention that there's an alternative way to implement this that I won't go into right now. Now, the reason why I spent so much time right now talking about this DSL is that it turns out that this DSL is not unique to Kotlin, or not unique to what I just demonstrated here, but it actually transcends languages, and different languages have different variants of this same thing that we talked about right now. So let's take a quick look at error handling in Rust. Now, before we go any further, I should say that I'm not a professional Rust developer. Like I read about it and I maybe played around it a little bit, but I'm not a professional Rust developer. So if any of you are, I hope I'm not going to be saying anything wrong. If you are, please feel free to correct me. So here's a very simple function in Rust. I hope you can see it a little bit. I translated it to Kotlin just so you have a better idea of what's going on. So Rust also defines a result type, same as I showed before, and it has the exact same, actually it has even the same names, OK and error, and it has the exact same semantics. And what we're doing over here is that we're taking some sort of file, we're opening it, and then we're reading a username from inside that file and returning it. Now, the key parts in this function, so you can see here we're opening the file. Here Rust does its thing, with passing with reference and stuff like that. So we're basically creating a string where we'll copy in the username, and then we're sending it into read to string. And the important parts are the question marks over here. Rust defines a question mark operator, and it's exactly the same thing that I talked about before, where I called it bind. So the semantics of this question mark operator is, if this function, if the file open, returns an error value, then kill the entire function and return that error value instead. But what's different to what we showed before is that while we implemented it like in an explicit way using Kotlin in this example, but it would work the same in Java and in any other language, here it's actually baked into the language. So this is actually syntax. This is not a function. This is baked in. Now there is one small difference between what I showed before and what's over here, and that's that we're explicitly wrapping the return value in an OK thing. Whereas here, in our example, here we go, we're actually doing this inside the inside the DSL, so we can only return the value itself, and it'll get wrapped for us. So that's one small change, but otherwise it's basically the exact same thing, and you can see the implementation over here in Kotlin. Now, Rust actually has another very nice feature that I like, and that is something that you run into very quickly, and I actually think there was a question about it even on the last presentation I made. Something you run into very quickly is that if you combine multiple functions which return different types of errors. So for instance, here we're opening a file that returns some sort of IO error if it fails, and here we're doing some calculation which returns a calculation error. So if we call bind over here, we get on a failure, we should be returning an IO error, but if we call bind over here on a failure, we should be returning a calculation error. But these two types aren't related, so what should we return? Now, does anybody, before I go on, does anybody have any idea how they would solve this? Or does anybody have any experience with this, maybe from their own programming?
You can map to your types,
Exactly.
or you can hope that new Kotlin with
Yeah, error unit and types for errors, exactly. Catch. Oh, sorry. Yeah, so that's exactly right. So this, by the way, is one of the reasons why checked exceptions in Java behave the way they do. So in Java, when you have checked exceptions, you can rethrow them in top-level functions without them actually having any common parent. So you can have an IO exception, a DB exception, and something completely else, and you can throw them all, and you're not required for them to have a common ancestor. And but when you're returning values, you don't have that luxury. And unless we'll have some special features in Kotlin, that's not something we'll be able to rely on. So basically, you have no other option than to explicitly map the values. So you have to go in over here. You have to bundle up open up the error type. You have to convert it to some common error type, and then rethrow it, quote unquote. Which is that's not great. But what Rust does is that they have a mechanism by way you can basically say that a certain error is convertible to another error. It's actually not related to error specifically. You can just say that one class is convertible to another. And you do that by implementing a trait which you can think of as an interface. It's called from, and you can basically say that a CLI error can be constructed from an IO error, and a CLI error can also be constructed from a parseInt error. And the way the question mark operator is defined is if you call it on a type, and the type doesn't correspond to the one you're returning from the function, it looks if it's not implementing that trait. And if it is, the trait that would allow it to convert from one to the other. And if it is, then it automatically calls it. So you don't have that boilerplate, that nuisance that you always have to be mapping errors from one to the other. Now, another thing that I really like about this, and that's why I actually don't really think of this as like a bad thing that you have to map those errors, is that it forces you to be explicit in the way what errors can be caused by which errors. And it forces you to model and think explicitly about the way you represent errors in your domain, which is something that I think is often overlooked. You spend a lot of time modeling the happy path domain, but you don't spend that much time modeling the error domain, and I think that's not a great thing. And I think checked exceptions went down the road of being easy to use, but I actually made it really easy to just rethrow all errors and let them all bubble up, and then you would have API calls at the very top level of your application that would throw 10 or 15 checked exceptions that would be something completely minute like parse error or something like that, and you would be like, why is this exception here on this level? So I think that this is very, and the way Rust does it, you actually immediately see right next to the definition of the class, you also see, oh, so this is a CLI error and it can be created from these two types of errors, and that actually tells me something about the way it's going to be used and something about the code without actually reading any specific code. So that's a specialty of Rust. Now, let's look at something a little more spicy. How many of you have ever read any Haskell? Not written, read. Cool, impressive. How many of you have written any Haskell? 8 years ago, twice maybe, or something like that. Nice, okay, that's not bad. So what I want to do for those of you who haven't, and for those of you who have, this will be you already know all of this, but for those of you who haven't, I want to expose you a little bit to this language, and this will be super simple, high level, and show you how it deals with error handling. So here we have some code. Again, I apologize for the screen size. I hope you can see at least a little bit. For those of you in the back, you can turn around and there's another screen over there if you can't see on this one. And what I did over here is I basically rewrote the domain that I was talking about before. I rewrote it in Haskell so I could sort of demonstrate the syntax and explain to you line by line what is actually happening here. So you see that it's actually not that complicated, even though Haskell is kind of a straszak for most people. So the first two lines start with new type. New type in Haskell is exactly the same as Is it value types or inline? Is it value classes or inline classes in Kotlin? I always forget which of the two it is. I think it's value classes. Value classes, right? Exactly. All of you get candy. So what that means is that I have one single data type that I'm wrapping. I get type safety. I'm actually creating a new type, but at runtime that type disappears and I don't have to pay for it. So that's what new type is in Haskell. So over here you can see I'm creating a new type, a value type of account ID, which is actually a string, but it's wrapped in a new type. Now data, just a data class. That's all it is. Over here you can see properties /getters / well, you don't have setters really in Haskell, but something similar. So you have an account, and an account has an account ID and a name. One is an account ID type, and the other one is a string type. That's what the double colons are. And the same with order and pricing. Again, nothing complicated. And finally, on the 8th line, type is actually a type alias. So this is, I think I had a slide over here at the very beginning. This is basically this type alias with a single generic parameter which resolves to a result. The important thing to know is that in Haskell, result is actually called either. So that's why you have either string, which is the string is the error type, and A is whatever we pass into the business result. So on the next, the 3 pairs of lines, we're defining methods. And the way you define functions, and the way you define functions is first you define the signature, and then you define the actual body. Undefined is the same as to do in Kotlin. It's exactly the same. You run it and it fails, but other than that, it type checks. And above that, you can see that this is a function that accepts an account ID and returns a business result of an account. Same as before. Same with get pricing, same with get order. So nothing complicated here. And now finally, we're getting to the števnatý part, to the interesting part. So here we have get account name, which means that we're getting an account ID. We want to retrieve an account using that account ID and then getting the name from that account. Now here it becomes interesting. So this is the signature of the function. So, and then we're starting with the actual body. So this part over here is the actual body. And here we see do and like backwards arrow. And do and backwards arrow are again exactly the same thing as I described before with the bind. So what this is actually saying, you can see it on the other side, is that we're doing get account, we're calling get account with an account ID, and we're extracting the value from that result, or from that either that comes in. And if it's an OK value, perfect, we're assigning it to account. If not, we're collapsing this entire block and returning that error. So exactly the same. You can almost, like if instead of the do you put bind over here, and instead of the arrow you put like an equal sign, you would get exactly the same code that you would in Kotlin. Now I will mention one sort of specialty of Haskell. This return over here, this is actually a function. This is not a keyword in the language. And what this function does is exactly what Rust does over here in the example, where it wraps it in that OK value. So return here is actually smart, and it knows that we're dealing with errors over here. It knows that we're dealing with either type. And so it therefore knows that it should wrap this part over here in an OK value. And that's actually one of the power of Haskell, because if we change this to not work with either, but for instance with a list, or a promise, or maybe some other data type, return would know how to wrap that into like that context without us actually having to change anything on the code, in the code. And that I think is when you talk to someone who like is really into functional programming and has experience with it, I think that this is one of the main arguments that you will probably hear, is that you can adapt code to very different situations without actually changing much else than the signature. And that I think is one of the big powers of functional programming. So that was one function. The other function, exactly the same thing. So we have a signature, we have the actual body. The body starts with do in the same way that our Kotlin version starts with result. It sort of denotes the DSL, but that's not what's really going on. And then we're extracting the order from this call, we're extracting the pricing from this call, and we're doing the multiplication and wrapping it in an OK value in the same way that Rust does it. Now, At this point, I will say that, and I sort of hinted at it before, this DSL in Haskell is actually much, much more powerful than what I showcased in Kotlin before. Like in Kotlin, you can only do error handling with it, nothing else. In Haskell, it's completely general, and you could deal with lists, and you could deal with promises, you could deal with various, like a very, very wide palette of different types. I won't go into that, but just so you know that this is much more general than what we're talking about here. Now, fun fact, knowing this, I think you probably know like 60–70% of Haskell syntax, period. Haskell is actually not a complicated language syntax-wise. It's complicated because of its standard library and because of the principles you need to understand when learning the standard library. But the language itself is actually, pretty easy to learn. Scala. Now, what's funny is that we can actually fly through this, because when you look at it just sort of visually, the way this is done in Scala is almost a copy-paste of the way it's done in Haskell, which is, not a coincidence, of course. So there are some differences. For instance, this is how you define value classes in Scala. You have to extend any val. Data classes are called case classes. That I think has something to do with, there's a historical reason why that's the case, but that's not important right now. The type, again, is a type alias. That's exactly the same. 3 question marks is the same as to-do or undefined. I actually really like that. 3 question marks is great. And then we get to the meat of the problem. But here, instead of having do and back rows and return, we have for. This is not a for cycle. This is actually not really for comprehension, maybe. I'm not even sure what you call it. But again, you have the back arrows. They do exactly the same thing. So you can imagine the dot bind over here that you would have in the Kotlin version. And the only difference here is that yield, which does the exact same thing like return that we talked about on the previous slide. This is actually a keyword in the language. So it's not a function. It's actually a keyword. But it's smart in the same way as the Haskell version, in the sense that over here it's very general, and we were not restricted to only using either types. We could be using lists and various other data types, and that has an impact on what this code gets evaluated to, but it's the same kind of code. Fun fact, you now know probably 4% of Scala syntax.
You also don't need to write a white paper to release a Scala.
Yes, that's true, and I think Scala is often the butt of jokes because of the fact that between Scala 2 and Scala 3, the research team basically closed themselves for 8 years in an ivory tower doing research. But that being said, I'm very strongly convinced that not revolution, but what's happening right now with Kotlin and error types, I'm pretty sure that would not exist if Scala didn't do the work that it did done. Maybe it did, I don't know that for a fact, that's just a gut feeling, but I think that we're benefiting from that investment. Now, this is a Kotlin meetup, so a natural question to ask is, can we do this in Kotlin? I mean, yeah, sure, we can write the DSL like I showed you, but is there a library that allows us to do that in Kotlin? And probably at least half of you know that, yes, of course, there is such a library. That library is called Arrow, and you can see that it defines exactly the same DSL that we talked about all this time. The only difference being is that Arrow uses the nomenclature, the names that Haskell and Scala uses, and not the nomenclature that Rust uses. So it uses either right and left, but otherwise you have the function is called bind. The raise over here that you say, that's the fail that we had at the beginning of the presentation. It's exactly the same thing. Now there are other things that you can do with the Arrow version. You can see there's a nullable thing here that I haven't talked about at all. It's very, it's basically the same principle, but just for nullable values, but we're not going to go down that road. I will mention, and we'll come back to at the end, there are actually 2 different DSLs in a sense that Arrow defines. One is the one we've been talking about right now, and the other one is hinted over here and relies on context receivers, and we'll come back to it in a second. Now, I want to quickly mention that Arrow is not, I feel like a lot of people think that it's like, if you want to do Haskell or Scala, but you don't write in Haskell or Scala, you use arrow, and that's true to a certain extent, but I would also like to mention that there's a lot more in arrow than just functional error handling. And I think that there is almost maybe even bigger value in this part of the library than the actual functional error handling. There are a lot of very cool things you can build based on the functions you have at your disposal here. So I really recommend you check that out in your free time. Okay. Now, there are a couple of big risks when you adopt this style of programming, but there's one in particular that's really easy to overlook, and it's really easy to let it bite yourself. Take a look at this code, hopefully you can see it, and tell me if you can see the mistake. There's a mistake in this code, a pretty big one.
Missing byte.
So two people basically at the same time. You have multiple desserts. Yes, exactly. You're missing the, you can't see it over here. The bind call over here is missing. Now, what this means is that if this happened to return an error, we'd just be swallowing it. We'd just go right through, we'd call this function, it would return an error, but we would just go on because we're not calling bind. So the account would get returned, and this we would never know. There would be no, because it's not an exception, there would be no stack trace, no nothing. Even worse, there are certain variants, and I think Arrow used to do this before with the effect DSL, for those of you who know. I don't know what the state is right now. Those were lazily evaluated. So this would sometimes, if you did this, not only would you swallow errors, you would actually not execute the function at all, which is a problem. And this is very easy to do, especially if you can see over here, these are functions returning unit. If they're functions returning some sort of value we need, then it's difficult to make that a mistake because you need to call the bind function in order to extract the value, and you need that value to do whatever you're doing inside the function. But when it's a unit returning function, you don't need it. So it's easy to miss the fact that you didn't call bind and you're not using that value. So how do you solve that? Well, tests, of course. The answer to everything are tests. The other answer that is not always realistic, but I try and adhere to it as much as possible. Always return values. Like, don't ideally. A function returning a unit basically means it's only doing a side effect. That to me is bordering on a code smell. I very much prefer functions that always return something, and that something is always used. And of course, static allows us to catch the fact that you're not using a return value. Now, you might reasonably ask, why is it that languages don't solve this on their own? Why is it that languages by themselves, or at least Kotlin, aren't designed so that they tell you, hey, you're not using this return value? And I won't go into it, but interestingly, this is actually a much more complicated problem than it seems. And if you're interested in it, I'll link in the end, or feel free to ask me in the questions. Okay. So, we talked about, or this entire time we were talking about DSLs that were based on extension functions. And the question is, are extension functions enough? Are the DSLs that we can express using extension functions everything that we can want? So take a look at this problem. Very simple problem. I have this repeating pattern in my code where I'm checking if a certain string is blank, and if it is, then I'm failing with some error that accepts the name of the property, so I don't have to duplicate that. And so naturally, I would want to extract this pattern and write code like this and be able to just take the getter and call cannot be blank on it. So how would I do that? Well, I can see that this is being called on the getter, which in Kotlin is kProperty, so I could define cannot be blank on it. And I could create a result type, or use the result DSL as I always did, and I would do the logic over here. But the problem is it's not quite what I wanted, because I still have to call the bind over here in the result class. And what I wanted is to not call it, is to just call the function itself. Now, I'm not saying this is a problem, like you could be completely fine with this and it would be okay, but just let's try to stretch our brain muscles. So let's say we really want to do that. So this doesn't work. Another way we could do it is, since we need to be able to call the bind or the fail inside this function, we can actually send in the result scope, which is the holder of the DSL verbs, inside of the function. And then we can call, fail and bind and whatever we want. But this leads to this really ugly code, which, we don't want that. This is really not nice. So that also doesn't work. And, the third and the only other possible thing we can do is basically switch these two input types. So instead define it as an extension function on result scope and accept the getter as as input. And this leads to this kind of code, which is actually really nice. This is like completely fine, but again, not quite what we wanted. So is the answer like, no, we can't write that type of code? And until recently, the answer was yes, unfortunately, you can't write that type of code, but that has changed. Because what you actually need in order to be able to write that code is you need to be able to define two different receivers. Now, this is pseudocode. This is not real Kotlin code. I'm just illustrating a principle here, where you want both the k property and the result scope to be part of the receiver, so they're passed automatically, and then you can call this type or write this type of code. And this is exactly why context receivers were implemented. Now, it should be said that the previous version of this presentation said that they were still experimental. As of about 2 or 3 weeks ago, they're actually deprecated, which was fun to find out. But they're actually deprecated in favor of something called context parameters, which is, for the purposes of this discussion, exactly the same thing. I didn't go do a deep dive on it yet, but the only difference that I can see so far is that they actually allow you to name the context parameters. That's basically the main difference. And this same principle, like Kotlin isn't the language that came up with this principle. The same principle has been in Scala for a very long time. It's called implicits. There are some differences in how they're resolved and stuff like that, but it's basically the same thing. So everything you're about to hear right now is still relevant. I'll be using context receivers everywhere. Just imagine I'm saying context parameters instead, and it'll work exactly the same. Now, this is not the way that it's defined. That was pseudocode. This is the way it's actually defined. So you have the main receiver over here, and then you define the context receiver or receivers over here in the context. I hope you can see it. Now, immediately we can see that since there are two different things we're sending in, we actually have two ways, or seemingly we have two different ways of writing this function. One is where the k property is part of the context receiver, or is inside the context receiver, and the result scope is the main, what we're defining it on, or the other way around. So the result scope is the context receiver, and the k property is the main receiver. Now, just based on gut feelings, like if you know context receivers, then you'll know this immediately. But even if you don't, just based on gut feelings, which of those two do you think is correct? And like both will compile. It's just like gut feeling. Which would you say is if you think it's the one on the right from your perspective, just point to the right. If you think it's on the left, point to the left. If you don't know, just leave your hand down. Nobody knows, really. To the right, one person knows. Two people know, 3 people know. Okay, to the right, perfect. Anybody think it's the one to the left? You're exactly right. It is the one to the right, and that sort of intuitively makes sense, because we're trying to define a function that runs in the context of some result type, or in the context of some result scope. So yes, absolutely, it's the one on the right. And actually, this is reflected nicely, because if you did do the one on the left, you would actually have to use with to move the k property inside the receiver space, or how I would call it, and this would lead to this ugly syntax. So immediately you can see that there's not only a semantic difference to what context receivers are versus normal receivers, but there's an actual syntax difference as well. It's not the same thing. So what you can say is that normal receivers that we all know are basically a way for us to offload passing of a parameter to the compiler, so we don't have to write it explicitly. And all context receivers do allow us additional parameters that we can offload to the compiler and let it pass for us. Now, can we use context receivers to make our DSL prettier? And the answer is yes. Yes, we can. So let's inspire ourselves from what we did before when we were, trying to make that change and simplify the DSL, and we tried those 3 different variants, and none of them worked out. And what we did over there is that instead of actually creating a new result object inside of our function, we're instead passing in the result scope of whoever is calling us and using that to do whatever error handling we want to do. So in this case, call bind, or maybe we would call fail, or something like that. But again, passing in the scope explicitly is not something that we want to do. That's not very nice. But now that we know about context receivers, we can solve that using context receivers. So we can define this function as being defined in the context of a result scope, and we can use all the functions that we have at our disposal. So this actually allows us to extend result scope without actually opening up the class. This is exactly the second DSL that I talked about before that Arrow defines. It's actually the more fundamental one, the one with bind that we were talking about most of the time, is actually defined on top of this raise, raise object. But it's exactly the same thing. So in Arrow, you can either use, either, and you can create the either object, and you can use bind, etc. Or you can define the function as having a context receiver of type raise, and then you can use those same functions inside as well, either raise or bind. Now, what this leads to, and here we're starting to get a little bit philosophical, but it's something that bugged me, because what this leads to is that you have two different choices. You have two different ways to approach error handling. One is where you actually create the object inside the function and return it. So the function that you're calling is returning an object that provides short-circuiting semantics. Whereas in the other approach, you're actually requiring that the caller passes in an object that has short-circuiting semantics. So there's a kind of duality where in one situation you're returning it out, and the other situation the caller is providing the function. So a natural question, or at least for me, was, so when should I use which? Is it like random? Is there some decision rule that I can use? Does anybody have an opinion on this? Probably more like if any of you have actually used Arrow, but anybody? Does anybody know when they should prefer one or the other?
When we want some make chain because we want inherit the higher scope into lower. That right approach with context receiver, because sometimes I don't want like return, but I want evolve outer or use outer scope, like for example,
Agreed.
I don't want to create local transaction, but I want to use outer and same this.
It's funny you mentioned transactions, because it almost looks like you saw this presentation before I'm about to presenting it. Yeah. So could you speak to? So you said sometimes I want to take or inherit the parent scope. I completely agree. Can you speak to when you would do that? Which situation you would want to inherit the scope, whereas which situations you want to create your own? It's a very gut feeling, like, I don't think there's an actual right answer to this. I will present an answer, that's my opinion, but you can disagree with it. But it's an interesting thing to think about. So, in other words, it's obviously not immediately clear when we should use which. So let's think of something else and see if we can figure out the answer to it. And what we're thinking about is transactions. So here's a simple problem that I think happens very often. You have some method, and you want to guarantee that that method is only called when a transaction is already opened. Now you can do that in Spring using the annotation transactional with the propagation sent to propagation mandatory, but this is runtime. So you won't get a compile time error when you write code that actually calls this function without a transaction being open. You have to actually run that code, call this function, and then you'll get the error. So the question is, can we make this compile time? Can we make this fail the build without actually having to run that code? And the answer is actually very simple. All you really need to do is, if you have some object that can only exist when a transaction is open, typically whatever the mechanism you use to open transactions, that'll probably return some sort of data object that represents the transaction. And you can just require in that function that that object is passed in. And at that point you get a compilation error, and the only way you can get your hands on that object is to actually create the transaction. But this is not ideal, because we're passing in an object that we might not even use. It's just there to prevent the error of calling this in a wrong context, but it's polluting the parameter list. People might get confused, like, why is this object here? It's unused. Static analysis will probably yell at us that we have an unused parameter. It's not ideal. But that being said, I've seen this used in like production grade code, not in Java but in PHP, and successfully. And it also kind of feels weird. But now that we have context receivers, we can actually fix this. We can actually define this as the context receiver. That means that the compiler will still check that we actually have this object in scope. But we don't have to explicitly pass it, so it's not an explicit part of the parameters, and it actually, kind of really reads well. Like when you look at this in the context of a transaction execution, oh yeah, that makes perfect sense. I immediately understand what the author was trying to say. So this is a very nice solution to this pattern of coding. Now notice that we again have two choices. The caller of getUser over here has two choices. One is it can create its own transaction and then use that object and pass it in, or it can itself require that it is called within a transaction. Now here I think, at least I hope, you should have a much clearer intuitive understanding of when you should use which. When should you open your own new transaction versus when should you require that a transaction is passed in? No ideas.
You want to have something atomic or like to fail together?
Interesting. Any other thoughts? So the way I think about this is that I think about who is owning the operation or the effect that's actually happening. So I'm asking, is the function I'm writing, is it part of a larger whole, or is it an actual whole in and of itself? If it's a whole, if it represents like a business operation or something like that, then it should probably open its own transaction. But if it's just some utility method that's just fetching something or just doing some small part of something else, then I probably don't want to be opening a transaction just for that. So I should be requiring that that transaction is passed in. So is this a whole versus is this part of a whole is the question that I should be asking. And when I do this, and I do this rigorously, it actually has an additional effect, and that is that I'm delimiting the boundaries of the operation. So I can immediately see when I'm looking at a function signature, is this function part of a whole, or is this actually doing its own thing, based on if it's defining its own transaction or if it's defined as a context receiver. And the exact same thing, or at least in my opinion, applies to error handling. So if you're doing something that's complex and sort of its own thing, then feel free to just create a new result and return it. But if it's just a utility function, like for instance the is not blank that we demonstrated before, then I would definitely go for the context receiver implementation. Now, I want to quickly mention something that's called Scala capabilities. It's basically almost exactly what we've been talking about right now. So dealing with how effects should be represented and how effect capabilities should be represented, and allowing functions to say I need certain capabilities in order to do my work, but expand it to a much sort of broader scope. Here you can see there's something called the can throw capability that actually allows a function to throw, and you need to provide the function explicitly that capability. But it's very generic in the sense that it's not, it could be the ability to do an HTTP call, or the ability to do an asynchronous function or something, asynchronous calculation or something like that. And this is currently being researched. It's like at the bleeding edge of what's being researched right now in this field, at least that I know of. There are some links at the end. I tried reading them. I failed. It's insanely complicated. There's a lot of math, but if that's somebody's cup of tea, then feel free to dive in. So I want to again emphasize this sort of duality between the two approaches that you can use when using Arrow or when using context receivers in general in Kotlin. So you have two basic approaches on how you can approach this. Either is that when you're calling a function, that function is returning an object that provides some sort of effect. In this case, it's error handling or short circuit semantics. And the other approach is that you require in the function that capability is passed in to the function. And there are some differences or some consequences to how your function, or how you can implement your function. So one thing you can do, and that actually I really like, when you build functions that return the result types, is that you can actually be pretty explicit about what that function is doing. So for those of you not versed in this style of writing, when you see this, you're like, boy, this is crazy. I would never want to write this. But for me, this is actually pretty great, because I haven't yet looked at the implementation. And I immediately, in 0 seconds, know that this function is going to do a database call. Based on that result, it's going to do the API call. So I know that it's in that order. It first does the DB call, then it does the API call. And that API call is going to return a list of orders. Now, I found out a lot about that function without actually reading anything. But what's even better is that this is basically documentation, but this documentation is enforced by the compiler. So when I change the code so that it does something different, this won't compile. And that means that it also saves me from some mistakes, like for instance, if I did things in the wrong order maybe or something like that, the compiler won't let me to write that code. And that's another thing that I think you will hear from proponents of functional programming is that it's much more difficult to write code in general, but it's much easier to write correct code. And I actually have first-hand experience with this where I wrote functional code in Java, no less, which was painful in and of its own. And it was a pretty complex thing that I worked on for like about a week or 10 days. The core of the application we're working on right now, and like it's not a simple thing, and it worked on the first try. Like that has never ever happened to me, the first try. And there's this thing that's often said between functional programmers, if it compiles it works. That's not 100% true, but it's very often true. So I really like this approach, but at the same time, when you actually call this function, at the end of the day, you're interested in either the list of the results or just whatever went wrong. You don't want to work with this super complicated nested thing. And so you actually have to collapse that structure. You have to take it and you have to transform it into whatever you want to do. And so that's extra work that you actually need to do as the caller of that method. Whereas if you use the context receiver approach, you don't have to do that. You're returning the list of orders immediately, and the effect is actually sort of collapsed in the background. So that can be another way of sort of deciding which of these two approaches you would want to use. Now, to that collapse I was talking about before, I'll just quickly mention that there are techniques on how you can do that when you have that super complicated nested thing and you want to just create something simple for it. So there's a whole I would say array of functions that you can use for it. I won't go into it. Again, if you're interested, you can ask at the beginning. So all in all, it's a trade-off between more information being more explicit, being more rigid, versus being more fluid and it being easier to write. Now, originally this presentation went on and it was sort of the halfway point, and I wanted to talk more about what you can do with context receivers, because I think there's a lot more interesting things you can do, but I'll leave that for another time because I think it would be too much for one presentation. So, quickly fly through what we talked about. We first talked about DSLs and the fact that they're actually nothing mysterious, and defining a DSL is nothing more than what we've already been doing all our lives, defining classes. And we can actually create a DSL for error handling, and it turns out that when we when we create an error handling DSL, it turns out to be the same way that many languages approach the problem of handling errors, specifically Rust, Haskell, and Scala, and there are probably some others. We also quickly talked about error and the fact that that's what you can use if you want to use this approach in Kotlin. And then we talked about context receivers and about the fact that it allows us to have more parameters that are automatically passed into a function without actually having to passing them explicitly. And they give us two ways to approach error handling. One where the function we're calling provides the capabilities to the caller, and the other where the caller provides the capabilities to the function. And we talked about how we can choose between the two. So here are some references. I'll send the presentation into Slack. For those of you who aren't members, then definitely join. The first one I want to mention is from Howard G. Cunningham. He's one of the co-authors of Agile Manifesto, and he implemented one of the first wikis. And he has a very nice discussion about why using exceptions as control flow primitives is bad, which is something that I mentioned at the beginning of the presentation. It's a very 90s page and a very 90s article, but it's a very good read. Another one I would definitely recommend is from Alexei Shipliev. I hope I'm pronouncing that correctly. His kink is going deep into the JVM and dissecting bytecode and looking how it translates to assembly code. And if you're interested in tuning your garbage collector or how the JVM does allocations or all kinds of this stuff, then he's the person to go to. And of course, he has an article on what makes exceptions expensive. Now here are some links to the documentation. The Haskell one, I will note that it assumes you already know Haskell, which is a little problematic, and it's actually hard to find pages about this that don't assume that. But today we have ChatGPT, and I think that if you're really dedicated, then you can definitely chew your way through that. I will also mention the Arrow homepage, not only because Arrow is a great library, but also because they have a lot of like introductory level articles about the whole topic of functional and error handling, which I think are interesting and good for beginners that like know nothing about this and don't know Scala and Haskell and want to delve into this a little bit more. And here are some final links. One of them is about the why languages don't actually catch the fact that you're not using a return value, and discussions about that. That's actually an open topic in the Kotlin issue tracker, and some things about transactional management and Scala. The final slide is, I talked with a principal developer at the place I'm working in not long ago, and he said something to the effect of, it's not worth learning a new language just because of syntax sugar. And I actually agreed with him at that point. And then I went back and I thought about this presentation and thought about everything I'm going to be talking about here. And I realized everything we're discussing here is nothing but syntax sugar. And I wanted to sort of emphasize that syntax sugar can really make all the difference in the world, and it's definitely a very good reason to learn a new language. That it's not all about functionality, but oftentimes it's only about form. Questions?
When would you suggest to use this cold style? Because my concern is, I come from functional languages like Erlang, Elixir, Clojure, and I'm hesitate to use this style in my Kotlin code because my coworkers will need to learn it, understand it, how to debug it, and stuff like that. So yes. I'm not sure.
That's good that you're not sure, and it's good that you're hesitant. I think that you need to be very careful about when you actually use this. So, like with everything, there's trade-offs involved, and you need to be aware of those trade-offs, and you need to know when you should pick the style and what you're going to be paying, for it. So this is what you mentioned is definitely what you'll be paying for it. Like, people will need to learn it. It'll be unfamiliar to people. There will be people who are unhappy because they don't want to learn, they don't want to change, etc., etc. But I would suggest using or thinking about using this approach when you need code that's absolutely 100% correct and you don't make mistakes. And I'm not talking about error handling specifically, but just generally writing things in a functional manner. What I mentioned before, writing that, that service where I wrote code nonstop for 10 days and at the end it just worked. That has never happened to me before, and I don't think it ever will. And I'm 100% sure that it's exactly because of that approach. And it wasn't like I finished writing and it worked. I finished writing and it didn't compile, but once it compiled, it actually worked. So you should think hard and discuss, of course, with your colleagues, is this something that we really need to be correct? And are we willing to pay for it with the onboarding costs, not just with your current team members, but with your future team members? Will we be able to deal with the emotions that this might screw up? Will we be able to deal with it if, for instance, you leave and they're without you? Will they be able to learn it? Will they be able to maintain it? These are definitely things that you need to keep in mind. And I would if you're unsure, then I wouldn't do it. That's what I would say.
So on that topic, is there a happy halfway? Can people meet halfway? Because what I've seen in practice, this exact thing with Scala. There was Scala imposed functional all the way. A few years down the line, it was totally apart. It wasn't worth the efficiency gain because people just knew Java, they knew Spring, and that's just the way to go. So, but I agree, and that speaks to what I'm even trying to do now with my code. But I feel for the sake of easy adoption, is there a happy middle path? Do you have to go all the way, what you've presented today, to make it worthwhile?
Well, I guess this also depends on where you want to actually go. So if all you really want to do is just error handling, I really don't think that it's very necessary to compromise there. You can explain what I explained here to a reasonably talented developer in 30 minutes, probably not even that. The mechanics of using bind, you can do that in 5 seconds. You don't need to understand functional theory to, you just do result and then you call bind and magic happens and that's it. You can do that very quickly. So I don't think it's necessary to compromise there. If you're talking about going down the functional programming rabbit hole, then two things. First thing, you should think about, are you actually using the right language? If that's the way you want to go, then maybe you shouldn't be using Java or Kotlin. But if for whatever reason, existing project, real world, whatever, if you want to go like to the deep end, I would say start with these simple things and then start reading. There's a problem that I've encountered, that there's a very wide gap between functional programming resources. Functional programming resources tend to fall into two categories. One category is super simple, trivial, basically what I was talking about here. Either, maybe the bind DSL, functional error handling, that's basically it. And then the other is, you need to have 4 PhDs to even understand the first sentence, like completely crazy, Clicey arrow, operators and stuff like that. And it's very difficult to find resources in the middle, resources that would explain like, what monads are or what applicatives are. I don't really think that you need PhDs to understand that. And I think it's not, easy to convey, but it's not complicated. It's just a different way of thinking. And that's why it's difficult to explain to programmers, because programmers, all they know is vegetables, and then suddenly you're talking about cars, and it's not that cars are complicated, it's just a completely different thing, and it takes some time to adjust. And I feel that the fact that there aren't resources that are filling this hole in the middle is a large part of that problem. Now, Arrow does, I think, a very good job of trying to at least sort of send you on the path, and that's basically where I started. Like, I learned Haskell before, I just didn't get it at all. I waited for 2 or 3 years, then I encountered Error. I sort of started sniffing around, learning a little, then I did a little more reading, and at one point it really all kind of clicked and it sort of seemed like easy. It's not perfect, like Arrow does have a tendency to like explain things in the way that it implemented it itself, and it's not really like it's, Scala does it different or Haskell does it different, but it's a good sort of starting point of where to start. And ChatGPT, as always, that's your friend. Like taking Haskell code or a Haskell article, taking the Haskell code and translate this to Kotlin or Kotlin like pseudocode, that really helps. That's something that we couldn't do 2 years ago, and it was a lot harder.
Any other questions? So I think that's it. Thank you very much, Gabriel.